motors, many molecular motors, and what we can try to do, we can try to understand the function of multiple motors working together by making models for a single motor. So last time I told you that if you have data, let's say experimental data on kinesin motor, okay, what you do, you find out its force velocity curve, right, and its force velocity curve, okay, and from that data, so let's say I have a data, okay, so I can fit a linear force velocity curve to it, and then I can fit a exponentially growing, exponentially decaying force, exponentially decaying force velocity relation. So my relation for force velocity will look like this, okay, and my force velocity will look like something like this. I mean, x is equal to x0 f1, right? So from the experimental data, in order to make a Monte Carlo model, we need to find out the probabilities of the events. Okay. So if there is just one event, then, and if I know the probability or rate of the event, then I generate a random number. If random number is less than that probability, then that event will happen. And similarly, Monte Carlo simulation also can handle multiple possibilities. Like if there are two events A and B, and if we know rates or probabilities of the events, then we can again generate a random number, and depending on the value of the random number, we can decide whether event A will happen or event B will happen or none of them will happen, right? So for kinesin motor, we saw that there are two possibilities: that it will step or it will detach from the track, and from the force velocity relation, we can get the stepping rate and force dissociation rate, right? And then I told you that when you are doing a Monte Carlo simulation, then there are certain rules to choose the time step, and time step has to be chosen such that your rate multiplied by this time delta t has to be very less than 1. Just make sure that only one event will occur within time delta t, right? And this delta t has to be chosen by keeping in mind the fastest reaction rate. For example, if a kinesin motor has a velocity of let's say 1000 nanometers per second, and it's taking a step of 8 nanometers, then maximum rate of stepping will be 125 per second, and similarly rate of dissociation will be roughly 2 per second. So the rate in this case, the delta t, the time step will be governed by the fastest rate. So if I multiply 125 by delta t is equal to 0.001, this gives me a number probability which will be very less than 1. Okay, and then I will do my simulation. Okay, so again we have two probabilities. One is the probability for stepping, and the other one is the probability for detachment. I will generate a random number. If my random number is less than, let's say, PS, then motor will step. And if it's greater than PS but less than PS plus PD, then motor will detach, and so on. And last time I also shared a code with you. So what I have done, I have emailed that code to Professor Kishanu Ray for this algorithm and the algorithm which I am going to tell you today. So just now. Okay. So I mean, if you want to get the code, you can get the code from him. So last time essentially we talked about the simulation of a stepping and detachment of single motor using simple Monte Carlo simulation. And today I am going to tell you about the Gillespie algorithm, which is an alternative way of doing the Monte Carlo simulation, and which is much faster. So my the whole idea is that you should be able to see the difference at the end of the talk, why it is faster. Okay. 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 So when we are doing a simple Monte Carlo simulation, right, we choose a time step delta t, right, and that delta t is determined by the fastest reaction rate, right. So suppose I have to simulate something for 60 seconds, and my time step is 0.001 second. How many times do I have to run the program to get this thing? 60 divided by 0.001. What will be that number? 60,000, right? So that means I have to, in order to complete a 60-second simulation, I have to run I have to do a iteration for 60,000 times, right? And every time when I will do this, I will check whether a stepping event can occur or not, whether a detachment event can occur or not. So I will have to do it 60,000 times, okay, when I am doing a computer simulation. So is there a better way to do this so that we can save some time? Yes, there is, and that is called Gillespie algorithm. Okay, so the way it works for Gillespie algorithm, that in the Gillespie method, what it does, it generates two random numbers instead of one random number. Okay, so it works on the principle that it first find out whether that event will happen or not. Like in the simple Monte Carlo simulation, what we are doing, that at each time step we are checking that whether motor will step or it will detach. Okay, what we will do in the Gillespie algorithm, we will try to see when a motor will step or it will detach. So that's the first difference. Okay, so instead of checking at every time step delta t whether motor will step or detach, we try to find out the time when either motor will step or detach. Okay, and then I will generate another number to find out which one of these events will happen. Okay, so the first thing is that when I will find out the time when the event will happen, it can be A or B, and then I will generate another random number to find out which of these events will happen, whether it will be A or B. Okay?
For the first one, you will be taking time scales. One will be for on, so there is a time of on and off conditions. Right?
No. So what I am saying that, so if I am doing Monte Carlo simulation, simple Monte Carlo simulation like we discussed last time. Okay? So I have some time delta t. Okay, right? I will start from t is equal to 0. Okay, then I will go to the next time, which will be t is equal to 0.001. Right? At this time I will check whether motor will step or not, and that I will do with probabilities Ps and let's say Pd, right? Which are determined by the rate of stepping and rate of dissociation. So I have to do this thing at every time step. T is equal to 0.001, t is equal to 0.002, and so on until I complete 60 seconds. Right? Now the difference in the Gillespie algorithm is that I will try to find out whether a motor will step or detach, okay, after how many time. So I am not doing this thing at every time step. I am just trying to find out the time when a step event or a detachment event will happen.
That will have two time points. So for time points, stepping will be different than time for dissociation.
What I am trying to, okay, so let's say there are two events A and B. Okay, so what I will try to do, first I will try to see when this event A or B will happen. Okay, so like for a motor, I will try to find out when motor will either step or detach. I don't care whether it will step or detach. So I will generate a random number, okay, which will determine when my motor will step or detach. Okay, and once I have determined the time when a motor will either step or detach, then I will generate another number to see whether it will step or detach. Okay, so it will complete that thing, right? So this is where I am saving time. So instead of checking for the things at every time step, I will find out when it will happen, and then I will choose which one of the events will happen. Fine. So the way to do it for the
events that have to happen, they might not happen at the same time. How can you predict that all these events will happen after so much time and then choose your events?
second.
So there may be 3 or 4 events that happen. How can you say that, okay, after so much time, an event will happen and it could be any of these events? Because it could happen on different probabilities at different times.
Right. So the method works as following. So first we find out the time when it will happen, A, B, C, or D. Okay, and then simulation. What we did, we had the rate of stepping. Okay, using that we found out the probability of stepping. We had the rate of detachment. Using that we found out the rate of detachment. Using that we found out the probability of detachment. Okay, and then my probability of detachment was, let's say, P, probability of stepping was PS multiplied by delta T, and probability of detachment was PD multiplied by delta T, right? So you see my older method, every time step I was checking whether PS will happen or PD will happen. Here what I will do, I will take the rates of stepping RA and RD. Using those rates, I will calculate at what time my next event will happen, whether it will be a detachment or stepping, I don't care. And then using the same rates RS and RD, I will calculate the probability of motor stepping, which will be the stepping probability divided by the total probability of all events. And similarly, for detachment, it will be the detachment rate divided by the sum of all the rates. Okay, so I can find out the probability of stepping and rate of stepping, and then I will generate another random number to find out which of these two will happen. Okay, so I will generate a random number, and if that random number is less than PS, then my motor will step, and if that random number is greater than let's say PS, then my motor will detach. So that's the difference. So the difference between these two methods is that in one method we check for the event happening at each time step, but in the Gillespie algorithm we check whether, we check at what time the next event will happen, and then we generate another number to find out which one of these events will happen. Clear? Any questions?
So in this model, you are executing the same steps and same events into two different steps. Means you are achieving the same goal.
Right, two different ways. Okay, and this method is faster because I don't have to wait. I don't have to do this thing at every delta T. Okay, because when you do this thing on computer, at each delta T you will write the sequence whether my motor will step or detach. Okay. Now in this model, if you use this method, then you do not do that. You have to write just one line when my next event will happen. Okay, and then you have to write another line which event will happen. So that will reduce your execution time. Okay, so I am going to tell you how efficient it is. Okay, so last night I did a simulation on my computer just to illustrate the method, and I have shared the code. Okay, so this code has been shared with you. Okay, so just wanted to tell you that it doesn't matter which method you use, you will get the same force velocity curve and from the same force velocity curve. You can verify it by running my program. The good thing here is that if I use the Monte Carlo method, the original Monte Carlo method which I discussed, okay, then my total real time which this program took for 65 steps or 60 seconds was 25 seconds. Okay, but if I use the Gillespie algorithm, how much is the time? About a second. So it got accelerated by 25 times. So this is the strength of this method, that I don't have to check for the event happening at each time step. I can just find out when my next time step will happen, and then I will find out which one of these events will happen, and you can get an acceleration. Clear? Huh.
If two events, two same events are happening one after the another.
Two same events?
Stepping. So suppose if I consider first event as to be stepping, the second event also to be stepping, then will the time scales to happen?
No. When you do Monte Carlo simulation, I told you the way to choose the time step is that you choose your P such that, you choose your probability such that it is very, very less than 1. Okay, so that is yours, that not more than one stepping event or detachment event will happen in that time into delta T, right? P will happen. So let's see how we will do it for muscular motor. Okay. So in the simple Monte Carlo simulation, what we did, we had the rate of stepping. Okay. Using that, we have found out the probability of stepping. We had the that we found out the probability of detachment. Okay, and then my probability of detachment was
probability of splitting was ES multiplied by delta T, and probability of detachment was PD multiplied by delta T, right? So my total method I will get every time step I was thinking whether it will happen or PD will happen. Here what I will do, I will take the rates of step RA and RB. Using those rates I will calculate at what time my next event will happen, whether it will get detachment or stepping, I don't care. And then using the same rates RS and RB, I will calculate the probability of total stepping. It will be the stepping probability divided by the total probability of all events. And similarly, for detachment, it will be the detachment rate divided by the sum of all the rates. Okay, so I can find out the probability of stepping and rate of stepping, and then I will generate another number to find out which of these two will happen. Okay, so I will generate a random number, and if that random number is less than 3, then my number will step, and if that random number is greater than less than 3, then my number will step. That's the difference. So the difference between these two is that in one method we check for the event happening at each time step, but in the Gillespie algorithm we check whether, we check at what time the next event will happen, and then we generate another number to find out which one of these events will happen. Clear? Any question? Right, two different ways. Okay, and this method is faster because I don't have to wait. I don't have to do this thing at every delta t. Okay, because when you do this thing on computer, each delta t you write a whether my total is less or is less. Okay. Now in this version, you use this method and you don't have to write. You write just one line when my next event will happen. Okay, and then you write another line which will happen. That is the execution line. Okay, so I will tell you how efficient it is. Okay, so last night I did the simulation on my computer just to illustrate the method, and I have shared the code. Okay, so this code has been shared with you. Okay, so just wanted to tell you that it doesn't matter which method you use, you will get the same code processing and the same code processor you will verify by running my program. The good thing here is that if I use the Monte Carlo method, the original Monte Carlo method, okay, then my total real time which this program took for 60 seconds was 25 seconds. Okay, but if I use the Gillespie algorithm, about a second, then you got a certain 5. So this is the strength of this method, that I don't have to check for the event happening at each time step. I can just find out when the time when my next time step will happen, and then I will find out which one of these will happen, and you can get an acceleration. Clear?
RS and RD are identical, what will happen? Is that your question?
So in the first formula, the R1 represents a stepping event.
No, R1 is a random number. See, at every time I am generating a random number to find out at what time the event will happen. So every time, so if you plot the distribution of timings, it will be an exponential distribution. Okay, so that will be a stochastic. So events will happen stochastically. Okay, it won't happen in the same amount. Like if I do it for the first time, it might happen in 0.002 seconds. Next time it will happen in 0.4 seconds. Next time it might happen in 0.0001 second. Okay, so it's completely stochastic. And this random number is just that. This kind of formula. How it comes, you will have to go back to paper to read this. And then I will generate another random number R2 to find out which one of these two will happen. Clear? Okay. So let me just very quickly do another thing. I think I will just flash the slides. So for example, Professor Peter Bass has talked a lot about very useful, right? So suppose you have to do a computer simulation with thousands microtubules, 1000 motors. Okay, it will take a huge amount of time. So if you use Gillespie algorithm, then you can get an acceleration. Okay, so this is really useful when you are dealing with really big systems. And in my last talk, I also talked about the dissociation kinetics of kinesin and dynein motor. And what I told you that these kinesin and dynein motors, if you try to pull them harder beyond the stall force, then their dissociation rates don't go up. Okay, as you pull them harder and harder. Okay, what has been observed for kinesin, it grows linearly, and for dynein, it decays. Okay, and this kind of behavior of dynein is called a catch bond behavior. And recently, a number of groups have reported the same thing. For example, we measured the detachment time of dynein motors in vitro and we found that it behaves like that. Similarly, George Subeta's group at UT Austin discovered the same thing. Manoj Gopalakrishnan and IIM Madras found the same thing using his theoretical approach. And then there is a recent paper by Roop's group in Cell, which also confirms this prediction in vivo. And what I wanted, so last time I discussed you about a qualitative model, like how a catch bond can be had. Okay, so there are various possible, conceptual models to understand this catch bond. Like if you have two hooks and if you try to pull them harder, it becomes very difficult to dissociate this kind of bond. Similarly, if you have toy, which is called finger tap, and if you try to pull your fingers out, it will stick inside that. And there is another conceptual model which is called deformation model. So it is based on the idea that if you are trying to pull the molecule, then this ligand will lock onto the receptor and it will make this bond very hard to break. And if you are interested into the biophysics of this thing, you can go back to this paper. This is a very nice article written by Gogol et al. In Annual Reviews of Biophysics. And in that paper they have presented biophysical models for slip bond, where basically you try to pull the molecule harder and it will dissociate. So how that can happen, and then how you can have a biophysical model for a catch bond. So I will stop here and thank you very much. If there are any questions, I will
We have a deep break now.
This is going to be very time, very long time. So we will take a half an hour to break and